Okay, so as I said, right, the one thing we can do to reduce the overhead of the translation is to have a cache called the TLB to basically cache the virtual page number, and you can get the physical page number out of that, right? So once you have the physical page number, you can plug in the page offset and you're done. You get your physical address, right? The other thing you can do is to increase the page size, right? So let's say you have 4 kilobyte page. It means that each TLB entry, each entry in your cache is going to cover 4 kilobyte region. So let's say you have 512 entries TLB, right? This will cover basically 2 megabyte region, which is somewhat small, right? Modern day computer like Linux also have a different solution called huge page, right? Which has a concept of physical frame number. The physical frame numbers basically cover a much bigger range. Usually with the OS right now, you cover the range of like 2 megabytes, for example. And then the page size can be adjusted based on the ISA or the OS. For example, the GPU would use a different page size, right? I think the modern day GPU, some of them use 64 kilobytes, some of them use 16 kilobytes, depending on some fine tuning optimization for each of the graphic cards that you buy. In general, but that's going to be a trade-off with huge page, because everything we do here, everything we do in system, everything we do in architecture has trade-off. So what are the trade-off with huge page, right? So now your TLB entry would cover a much bigger range. For example, if it's 2 megabytes, it means that the TLB entry, one entry would cover 2 megabytes. So let's say you have a really small TLB with even things like 16 entry, you can then cover 32 megabyte region, which is a lot more, right? But here are some key problems. So previous paper, like this InGen paper in OSCI 2016, talks about the fragmentation problem where when you sweep over the time, right? Over time, your workload, which in this case is Redis, right? When you use huge page, your memory gets super fragmented in a sense that you have allocation, deallocation, allocation, deallocation, and you end up with so many holes that you cannot really fill in unless you move things around and compact them together. You also have this problem of, let's say you have to kick something out of your memory and you need to figure out which page do you want to kick out. If you use huge page, it means that you kick out 2 megabyte region, which means that you can't really tell again which page you want to kick out. Let's say you have a hot pages that get touched, but you only get touched like 4 kilobytes out of those 2 megabytes, right? In that case, that whole thing is marked as hot, so you keep the whole thing. And also the promotion demotion policy is also a big problem, as shown here in this plot, again, from the InGen paper. You run 3 VMs over time, and you can see that the huge page consumption is only going to VM3. It's quite unfair, right? One of the main problems is fidelity loss in huge page. So I'll explain this problem a little bit because it's one of my research that we published in 2020 with VMware. So let's say you want to maintain the cleanliness of the building. So this is a Willis Tower in Chicago, right? And let's say I want to use small page. I can compare this to, let's say the window is dirty on the tower, right? But because I can see that that one small pane of window is dirty, so I'm gonna go and clean that, right? But then, what if I have large page? A large page, and the same case, like you have one Windows pane that's dirty, and I need to clean that. But the problem with large page is I track this whole site, but I have no way to track each individual Windows pane, so I can't tell what part of this site is dirty, so I need to clean the whole thing, right? So I need to clean the whole thing. So that's one of the big problem in a huge page that you run into right now. So I'll talk about my research later. Now let's go to the second solution. So the first solution is using a TLB, and you can also extend the range of the TLB with large page. The second solution is you can also cache. So you don't cache the whole thing. You don't cache VPN to get PPN. You can cache only parts of it because page table is 4 levels deep. Modern day CPU has 4 levels deep, right? So here's the page walk process. So this is level 1. So that's the first table, right? Then you go to level 2, which is the second table, which span into level 3, which span into level 4, right? So this level 3 and this level 4. Instead of caching this whole thing, so TLB would cache the whole thing from here to here, right? So this is what the TLB would do. The page walk cache will only skip some level from here down to here. So this is a page walk cache. It means that you still can skip some level, but then at the end of the day, you need to do the translation. So the benefit is it has a much higher coverage, and you can catch partial translation data. And both Intel and AMD processors deploy both TLB and the page walk cache to make sure that you run into only a few cases of going through 4 levels of page walk, right? And the page walk cache structure, right? So basically you have the virtual address coming in. You would then compare the level 1 index, right? Level 2, and see how far can you skip, right? So that you can get to as close to the leaf node as possible. But in general, you want to avoid page walk because they're expensive, right? So in the end, you can use the combination of these 3 solutions and many other things that we have, like human, as in like a human as the whole, right, has been proposing so far in the last 20 years to try to hide and make the effective use of TLB, page walk cache. Even things like, can we change the page table structure from a tree-like thing to something else? So there's also like some GPU side optimization, which I'll talk about in the future as well. Now, here comes the second solution, right? The second solution is in many modern design, you cannot access the cache without knowing the physical address, Why? So the key here is when you look at caching, right? You have 2 things. You have the index bits and the tag bits that comes from your address. So when you use cache, you have the tag and you have the index. So when you look at your address, which I'm not telling whether it's a virtual or physical address yet, right? So this will be the byte in block bits. This is the index bits. And this is the tag bit. You need to figure out, do I want to use the virtual address for the index bit or the tag bit? Do I want to use the physical address for the index and the tag bits or not? And you have basically 4 choices. You can have physically indexed, means that I use physical address for the index bit. Physically tagged, also use physical address for the tag bits. PIPT, which is virtually indexed, physically tagged, use virtual address for the index bits, and then use physical address for the tag bit, and VIPT. Now let me motivate what can go wrong with each of these options and which one is the best option. First of all, you can have this thing called Homonym Problem. 2 different programs, Google Chrome and Microsoft Office, for example, can have the same virtual address because it's just a virtual address. It's just a nickname for your physical address. But because there are 2 different programs, so they are mapped to 2 different locations, this is called Homonym Problem. Now, let me ask you this. If I need to tell the difference between virtual address 1 and virtual address 2, but VA1 equals VA2, how do I do that? Because I need to make sure they have different, because they have different physical address. So this is PA1 and this is PA2. But in this case, PA1 is doesn't equal to PA2. So how do I do this? How do I fix this? The tag will then need to be able to tell the difference between the two, which means that if I want to tell the difference between these two addresses and I use the virtual address, can I tell any difference? Do I ended up with the same tag? So let me ask you this. Do I ended up with the same tag if I use virtual address for the tag? Again, VA1 equals VA2. So if I extract the tag bit from my virtual address, will I ended up with the same tag from Microsoft Word and Chrome? Again, I have the mapping, right? So I can have a valid virtual address from two different applications. It just happens to be the same value, but they go to a different location because it's two different applications. So it has two different physical address. So in this case, right, if I use virtual address for the tag, I will end up with the same tag, which means that if I go look up the cache, I cannot tell the difference. Then I cannot tell, is that data Google Chrome or is that Microsoft Office data, right? So in this case, can someone tell me, is it okay then if I use virtual address for physical address, my bad, if I use physical address for the tag bits, is that okay? So is it okay if I use physical address for the tag bits?ถามใหม่เป็นภาษาไทยก็คือว่าผมบอกว่าสมมุติผมมีโปรแกรม2 อันอาจจะ Google Chrome อันหนึ่งแล้วก็ Microsoft Office อีกอันหนึ่งรันอยู่มันก็ดันขอมาล็อกแล้วมันได้ virtual address ค่าเดียวกันใช่ค่ะได้ค่าเดียวกันเลยแต่ว่ามัน physical address มันไม่เหมือนกันอยู่แล้วเพราะว่ามันเป็นโปรแกรม2 โปรแกรมที่มันรันคู่กันอยู่ในกรณีนี้เนี่ยถ้าผมคือ cache อะเวลาผมจะ search ของว่า data ผมอยู่ใน cache หรือเปล่าอะผมสามารถใช้ virtual address มาเช็คหรือ physical address มาเช็คก็ได้มันเป็น choice ของผมเนาะถ้าผมใช้ virtual address สำหรับ tag bit อะมันจะมีปัญหาก็คือว่าเพราะว่า virtual address จาก2 โปรแกรมนี้มันดันบังเอิญเป็นตัวเดียวกันเดะเลยผมก็จะได้ tag เดียวกันแล้ว tag ใน cache เนี่ยมันเป็นเหมือน identity ของเราว่า data ชิ้นนี้ใครเป็นเจ้าของแต่ด้วยความที่มันซวยมันเจอ tag เดียวกันเลยอ่ะมันก็จะตอบไม่ได้ว่าอันนี้คือ data ของ Google Chrome หรือว่ามันเป็น data ของ Microsoft Office เพราะฉะนั้นผมเลยต้องใช้ physical address เพื่อเป็น tag bit อันนี้ตามทันไหมครับมีใครมีคำถามหรือเปล่าใช่มันใช้ได้ทั้งคู่ก็คือมันเป็น choice ของคนดีไซน์เครื่องไงแต่ว่าถามว่ามันใช้ได้ทั้งคู่จริงๆไหมคือถ้าเราใช้ virtual address เป็น tag อ่ะคราวนี้มันก็จะมีสิทธิ์ตุ้มตามได้เพราะว่าเรามี virtual address ที่ซ้ำกันได้คือมันก็มีเปเปอร์จริงๆมันมีเปเปอร์ที่บอกว่างั้นเราก็ make sure ว่า OS จะไม่ assign virtual address ตัวเดียวกันมาให้สิเพราะเรามี64 บิต64 บิต range ก็กว้างไกลอย่าก็แค่การันตีว่าอย่าให้มันซ้ำกันแล้วเราก็ใช้ virtual address เป็น tag ก็ได้เหมือนกันก็เป็นเทคนิคแบบหนึ่งที่ทำได้แต่ว่าถ้าเราแบบไปอ่าน textbook เนาะว่า CPU ปัจจุบันมันใช้ยังไงก็คือมันจะใช้ physical address เป็น tag เพราะว่ามันเพื่อการันตีว่ามันเป็น unique address แน่ๆนะครับอ่ะ Well, that's the homonym problem where you have the same virtual address but two different physical address. Synonym problem is the inverse of that. Two virtual address can be mapped to the same physical address. Like somehow you have sharing, for example. This is called synonym problems. And in the end, right, you want to also be able to tell the difference between the two. We will not talk about the synonym problem as like what is the solution to that yet because you have to do things like page coloring. which is more like a system technique. But now we focus on the homonym problem, the earlier problem. One virtual address go to two different physical address. So now let's ask this question again. I have four options. Which one doesn't work? Anything that use virtual tag, right? This thing doesn't work because it's used virtual tag. So you only have these two options left, PIPT and VIPT. Now let's go to the two things and discuss, are there any issue? For example, are there issue with PIPT? PIPT means that I need the physical address before even checking out the cache, right? So this is what essentially what I'm trying to say here. So this is your address, right? Which I use the index and the tag. And here's your cache, right? Cache. The first thing you do is you get the index bit, right, into here to search for the set, right? Over here you use index bit to get the cache set, which basically looks like this. You have the set with multiple cache block 1, cache block 2, cache block 3, and cache block 4, for example. And then you use the tag bit to compare whether the tag from your address equal to any of the cache block or not. And let's say it match with the cache block here. So let's say the tag match here. Means that it's a cache hit, right? So this means that the whole process starting from here, this has to be physical address. This has to be physical address, which means that I need physical address to go to the cache to get the set. Then I will compare the tag. So I do VA into PA to get cache set, then compare tag. Right. So that's my process. I need to do this serialization. It's sequential process. VIPT is not possible then because you then run into the homonym problem. VIPT you run into the homonym problem. How about VIPT? When you look up, right? When you look up, so you have virtual address, right? You take the index bit here. Index bit to go to the cache, right? To get the cache set. Then at the same time, you use VA to go to the TLB, right? To get your physical address. Once you have the physical address, then everything here, you compare the tag. In order to get your data. So in this way, you overlap the time you go to the cache set with the time you do the translation by checking the TLB for your physical address. So this is faster. Basically, this is faster than PIPT. All right. So you can use physical address to check the tag, and that's okay. It eliminates the homonym problem. The benefit is you now overlap, right? You overlap the latency of TLB lookup. And the downside, you want to make sure that it's the TLB hit, right? And let's say if your data is not in the memory, right? So virtual address can also provide, so this is the last benefit of the virtual address. It can also provide virtually larger memory than VRAM. Than the page that are not used often, they often kick out to the storage like hard disk or SSD. If the page does not access, that we want to access not in DRAM, we call this a page fault. So if you read textbook and you see the word page fault, it basically means that I want to find some data and they're not currently translatable to somewhere in DRAM. Then the remedy is to then you retrieve the page from the storage, and this takes a long time, right? To deal with the synonym problem where you have two virtual address mapped to one physical address, some solution is you can limit the cache size so that index part is from page offset. Why? Because page offset is the same for VA and PA. So if you do that, if the index bit come from the page offset, it guarantees that both virtual address and physical address has to be the same, right? You can also search all possible indices to contain the physical that contain the physical block, or do the page coloring, which means that you restrict where the page for each of the processes go to. So that's ensure that the index bit for virtual address and the index bit for the physical address is the same. So that they map to the same location. This allows the case because it's the same address, it's the same physical address. But if you use virtually indexed, basically if you use virtually indexed cache, right? It means that you have VA1 and VA2 that has two different values, but it's the same physical address. It's actually the same exact data, so you can use the cache. But because if the index bit come from the part that not from the physical address like a page offset, it then means that I will have a cache miss. Unnecessarily, it's actually a cache hit, right? แปลเป็นไทยนิดนึงนะครับก็คือกรณี synonym เนี่ยมันเป็น data ชิ้นเดียวกันเพราะมันเป็น physical address ตัวเดียวกันแต่ว่าด้วยความที่มันมาจาก2โปรแกรม2โปรแกรมที่มันรันหลุดแล้วมันอาจจะแชร์ data กันก็คือมันมี virtual address 2ตัวแต่มันคือ data ชิ้นเดียวกันถ้าผมใช้ VIPT นะมันบอกว่าผมจะเอา index bit มาจาก virtual address แปลว่าอะไรถ้า virtual address ที่ไม่เหมือนกันมันก็จะไปที่คนละเซตกันก็แปลว่าผมมี data ชิ้นเดียวกันแต่แม่งอยู่คนละเซต1กับเซต8สมมติแล้วมันเป็น data ชิ้นเดียวกันคือผมต้องการบังคับให้มันอยู่ที่เดียวกันเพราะมันเป็น data ชิ้นเดียวกันคือถ้าเรามี lookup ที่มาจาก2 virtual address อันเนี้ยมันจะได้วิ่งไปที่บล็อกเดียวกันคือวิธีการทำของ OS ก็คือเราก็ต้อง limit scope ของการใช้ index bit ให้มันมาจากส่วนที่เป็น page offset ก็ทำได้เพราะว่า page offset ของใน virtual address กับ page offset ของ physical address มันการันตีว่าจะเป็นตัวเดียวกันเพราะฉะนั้นคราวนี้พาร์ทนั้นพาร์ท index คือเราต้องการ force ให้แบบว่าพาร์ทที่เป็น index bit เนาะของแอป1เท่ากับ index bit ของแอป2ซึ่งเราก็แค่ต้อง enforce condition นี้ให้ได้นะครับ so that's the synonym problem and then the third benefit is memory protection basically when you do translation right the page table entry as I said it contains permission bits such as things like address space ID who owns this particular range of address if it doesn't match access violation so you get seg fault when you run C code whether this is read or write versus read-only bit. So if you try to modify read-only pages, again, we have illegal access, which would trigger the OS to warn the user, something is wrong here. Let's take a look at that. You, as a user application, try to modify the supervisor or super user application. That's also a problem, right? Because that's illegal access. So these are what virtual address give you. Basically, it protects the data from illegal access. And now let me wrap everything together. So let's say you have a pointer in your C program, and let's look at what happened when you try to access your pointer. So let's say you have int star I, right? And let's say this point to a place in DRAM that has the value 20. That's the address of I. Basically, I have one pointer. It points to the value 20. What happened when I want to read that? When I want to read that value 20? For a day in life of my data access, on the left side, I have my CPU right here. So this part is also in the CPU. Everything from the left here is fast to access. And these are the slow things, right, in the DRAM. So from your processor, the top part is anything that related to the data cache, like the L1, L2, and the last level cache. The bottom part is the translation structure, like the TLB, and the memory management unit that perform the page walk. And you have the load address. I want to read my data. What happened? I'll take the index bit from the virtual address to check the L1 cache. At the same time, I'll take the virtual page number, VPN, to check the TLB. And if my VPN is in a TLB, it means I can get the physical address, which means that I can use it as the tag bit. Then I'll look at the L1 cache and see if my data is there or not. If I miss in a TLB, then I have to do the page walk by going to the page table 4 times for a 4-level page table in x86 CPU, like Intel and AMD chips that you have nowadays. So you now go to DRAM 4 times to get the physical address in order to get the tag bits, so you can access the L1 cache. Now we are not at the data yet, right? So let's say it missed in the L1 cache, you then go to the L2. If it missed in the L2, you go to the last level cache, and you don't have the data in the last level cache, you use the physical address to get the data in DRAM, right? To get the data in DRAM. And physical address is basically PPN append with the page offset. So that's where your data is, the value 20 for address I. All right. So let me take a quick pause here because that's the end of the more like a textbook material. I'll talk about virtual memory design and what happened inside the virtual machines coming up next. Now I'll take some question มีคำถามไหมครับ อันนี้สไลด์นี้ก็คือแบบว่าบอกว่าถ้าสมมุติผมมี data access 1 อันมันมีอะไรเกิดขึ้นบ้างจนถึง DRAM ซึ่งก็คือเป็นที่ที่ผมเก็บ data ไว้นะครับสเต็ปแรกมันก็เอา virtual address ของเราเนี่ยมันจะดึง index bit มาก่อนแล้วไปดึง cache set อันนั้นออกมาทั้งเซตเลยก็คือมีกี่ cache block ก็ไม่เป็นไรก็ดึงมาก่อนและระหว่างนั้นมันจะเอา virtual page number จาก virtual address เราเนี่ยแหละไปเช็คใน TLB แล้วดูว่าเรามี physical page number cache ไว้ใน TLB หรือเปล่าถ้ามีก็จะได้ physical address แล้วเราก็ไปเช็ค tag bit แล้วก็ดูว่า data อยู่ใน cache หรือเปล่าถ้าอยู่ก็เย่ถ้าไม่อยู่ก็ไปต่อไป level 2 cache ไป last level cache แล้วก็ไป DRAM แต่ถ้า virtual page number ของเราไม่อยู่ใน TLB ก็คือเราต้องทำ page walk ก็คือเราต้องวิ่งไปที่ page table 4 รอบเพื่อเอา physical address เพื่อพอได้ physical address ไปแล้วมันจะกลายเป็น tag bit ของ cache เวลาเรา look up ทำ look up ใน cache เราดูว่า tag ตรงหรือเปล่าเพื่อที่จะดูว่า data เราอยู่ใน cache หรือเปล่าแล้วก็ถ้าไม่อยู่ก็ค่อยไปที่ DRAM นะครับก็แปลว่าถ้าเรามีโหลดชิ้นหนึ่งใน instruction ต้องการโหลดอะไรสักอย่างใน memory มีได้หลายกรณี TLB hit L1 hit TLB hit L2 hit TLB hit last level cache hit TLB hit ต้องไปที่ DRAM เพื่อแปล data ก็1 DRAM access ถ้า TLB miss ก็แปลว่าต้อง4 access เพื่อไปที่ page table ก่อนที่จะได้ physical address แล้วก็ไปดูใน L1 L2 แล้วก็ last level cache แล้วก็ DRAM ต่อไปนะครับสรุปก็คร่าวๆตามนี้นะครับเดี๋ยวผมขอรอบนี้จะเบรกเยอะนิดนึงเพราะว่าตัวอย่างค่อนข้างเยอะนะครับเดี๋ยวขอเบรกก่อนก็ขอ stop recording ก่อนนะครับ